Hi and welcome to this section where we are going to look at a vector space. Now, a vector space describes the relationship between two sets. One set we shall call V and the other is F, okay, together with two algebraic operations, and that is vector addition together with two algebraic operations, vector addition and scalar multiplication. Okay, now V is going to be, or is a non-empty set of objects called vectors, while F is a scalar field. For instance, it can be the sets of reals or the sets of complex valued numbers. Or it can be real valued or complex value. This is real and then this is complex. So a vector space is going to give us the relationship between a set of vectors and the scalar field F, okay, together with two operations, that is vector addition and scalar multiplication. So vector addition, maybe we can have x plus y, okay, where x and y are both vectors, they are taken from the space V. And then scalar multiplication, for example, we can have and it's something like alpha times x, of course, where alpha is either taken from real valued or complex valued, and then x is taken from the vector, okay, from the vector space here. So now that we have laid some background info, we are going to go on to define. So we say that the set V, okay, is called a vector space. The set V is called a vector space over F. Space V is called a vector space over F, okay, when the vector addition and scalar multiplication satisfy the following properties. Okay, so we are going to set down the following properties. So we shall denote the ones which are addition by A. So when we say A1, it will mean the first one for addition, okay? So what was the first one tell us? It tells us x plus y, okay? Okay, in other words, if we have x plus y is, okay, let us just state like this, that we have x, y and z, which are vectors from V. Then A1 tells us that x plus y is also the sum of two vectors. If a vector x is a member of the vector space V and y is also from the same vector space, then their addition also belongs to the same space, okay? For example, I can give a very simple example, is that maybe if this vector space is the space of real numbers, then maybe if the sum of real number, if you get a real number and you get another real number, then their sum is also like a real number, okay, something like that. But we shall give some of these proper examples later on. Okay, so what else? Okay, This is x plus y is also taken from V, and this is what they call the closure property. The closure what? Property. Okay? For vector addition, the closure property for vector addition. A vector x taken from V and another vector y taken from V, then their sum is also taken from V. Okay? What about A2? A2, we have this associativity that x plus y plus z is the same as x plus y. I mean x plus y plus z, and then here x plus y plus z. Okay, that is for every. This is for every x. Okay, maybe we can say here for every x, y, and z taken from V. This one here holds for all x, y taken from V. What about A3? A3 tells us that x plus y is the same as y plus x. Okay, that is for every x and y taken from V. Commutativity holds for addition. So F4 tells us that there is an element or 0 which is taken from V. Okay, there exists the 0 vector taken from V such that x plus 0 is the same as x. Okay, for every x taken from V. Okay, there's the fifth one here. And then what does the fifth one say? The fifth one says that there exists an element, okay, negative x, which is taken from V for each x. Actually, we say that for each x taken from V, we have its additive inverse, that is negative x, taken from V, such that x plus its additive inverse gives us the 0 vector. And then we quickly move on to the ones for multiplication. Okay, so multiplication tells us that alpha x, the product, is also taken from V, that is for all alpha which is taken from F. Okay, and x taken from V. Okay, then the product is also from V. Okay, and this is the closure property for with scalar multiplication. Then 2, associativity also holds here, so we shall say that alpha times beta times x is the same as saying alpha then times beta x. Okay, of course here we have alpha and x taken from the vector space, and then alpha beta taken from the field F. Okay, what else? That is M2, and then we have for M3, okay, this distributive alpha x plus y is the same as alpha x plus alpha y. We have for x and y taken from V, and then alpha taken from F. So what does M4 tells us? M4 tells us that alpha plus beta times x is the same as alpha x plus beta x. Again, for x taken from V, and then alpha beta taken from F. What is M5? M5 tells us that there exists the identity such that 1 times x equals to x for every x taken from V. Okay, so if you have these properties here satisfied, then we have that the set V is a vector space over F. Okay, when vector addition and scalar multiplication satisfy A1 up to F5, for that is vector addition, and then m1 up to m5 for scalar multiplication. So let us bring this nearer to us by looking at some few examples. All right, now for some examples here, we are going to say that the set, okay, of matrices which are real valued, the set of real valued matrices are of order m times n, okay, of m by n real matrices, okay, is a vector space over R, the set of reals. Now, it is a trivial exercise for you to actually show that this vector field V, which we are calling now this vector space V, which is the space of all real valued matrices of order m by n, is a vector field, okay, is a vector space. So I keep on saying field and space, but let us stick to space. Field means something very different. Okay, that vector, the set of this vector space here of matrices m by n is a vector space over the set of these real numbers here. Okay, in other words, you can actually show that a1 up to a5 holds. In other words, if you get a matrix, let us say maybe this is a 3 by 2 matrix. Since it is m by n, this is a 3 by 2 matrix, this is a 3 by 2 matrix. So if you add them, the result is also what? A matrix. Okay, associativity holds for matrices, doesn't it? Commutativity holds for matrix addition. Not so. There exists the zero matrix. The zero matrix, the matrix full of all zeros, such that you can add, we say this is 3 by 2, okay, such that you can add them to the matrix which we have, and then we get the same matrix, right? And then there also exists this additive inverse. In other words, the matrix of negatives which you can add to the matrix itself, because you know that negative a plus a will give us the 0 what matrix. And then you can actually also show that for any matrix of that order, okay, maybe you can just say an arbitrary matrix a, b, c, d, or anything of that sort, okay, e, f, anything you want. You can show that actually this holds. Scalar multiplication, you multiply a scalar with a matrix, the result is still a matrix. You can multiply two scalars with the matrix. You can get the order here, does not matter whether it is alpha times beta then times the matrix, or you first multiply this beta times the matrix and then times alpha, the result is still a matrix. And then you can also show that M3 holds, and even M4 holds for matrices. And then also for matrices, you have the identity matrix. It exists, which you can multiply with the matrix itself, and it does not change the result, okay? So if it is a 3 by 2, you can find our matrix here. I'm not so sure. They said the identity matrix of order n, the identity matrix, we can multiply it. Okay, in that case, I think it will have to be a square matrix if we are going to deal with the identity matrix. I will clear this shortly. Okay, maybe do we have any other another example with this which is similar to this? Yes, we have also here the set. Yeah, more or less the same. It is the set of complex valued matrices is a vector space over C, the space of also complex numbers here. We can actually also follow through the same steps, and then we come up to that. So what is not so clear here is this identity matrix, because the identity matrix will have to be a square matrix. So I'm not so sure in that case, I think, but they say that for every x taken from V. Okay, I will clear this at the beginning of the very next video series. I would like to stop it for now so that we do not get into time while I'm thinking on job here. Let me think about it off the video, and then in the start of the next video I will clarify this. Okay, thank you and see you in the next video.